Space debris and the Kessler syndrome risk. Why orbit is becoming fragile infrastructure. Space debris is the collection of dead satellites, rocket fragments, and collision shrapnel orbiting Earth at extreme speed. People search for it because satellites feel invisible until something goes wrong. Navigation. Glitches, missing imagery, lost communications, or a sudden headline about a near miss. The tension is that orbit is both enormous and crowded. A single collision can create thousands of new fragments, and those fragments can trigger further collisions. That cascading risk is often called the Kessler syndrome. This guide explains what space debris is, why the risk is growing, what can be done, and what safe orbit really means in a world of mega constellations. The story turns on whether orbital growth stays manageable or tips into a self-reinforcing debris problem. Key points. Space debris is dangerous because objects in orbit move fast enough that even small fragments can destroy satellites. The Kessler syndrome is the fear of a cascade. Collisions create debris. Debris increases collision risk, and the environment worsens over time. The highest operational risk concentrates in specific altitude bands and heavily used orbits, not evenly across space. Tracking and collision avoidance help, but they do not solve the long-term problem of dead objects that cannot maneuver. The incentives are misaligned, the cost of cleanup is private, while the benefit is shared by everyone using orbit. Practical progress depends on disposal rules, better tracking, transparent coordination, and eventually removing the most dangerous large debris. Background: space debris. Low Earth orbit, LEO, is the region closest to Earth where many satellites operate. It is popular because it offers low latency and strong signals, but it is also the busiest zone. Medium Earth orbit, MEO, hosts navigation satellite constellations. Geostationary orbit, GEO, is a high orbit where satellites match Earth's rotation and appear fixed over one spot, often used for communications. A conjunction is a close approach between objects in orbit. Collision avoidance means maneuvering an active satellite to reduce risk when conjunction predictions cross thresholds. Space debris includes defunct satellites, rocket bodies, fragments from explosions, fragments from collisions, and tiny paint flecks and bolts. Not all debris is trackable, which is part of the danger. The Kessler syndrome is the idea that a debris environment can become self-worsening if collisions produce enough new fragments to raise collision probabilities faster than debris naturally decays out of orbit. Deep dive: space debris and Kessler syndrome. How it works, mechanism or logic. Orbit is a speed problem. Objects in LEO can pass each other at several miles per second. At that speed, a bolt can strike with the force of a grenade and a satellite. Collision can resemble a shotgun blast dispersed throughout an orbital band. Collision risk rises when three factors combine: more objects, limited maneuvering, and imperfect information. More objects increases the number of possible encounters. Limited maneuvering matters because many objects are dead, they cannot dodge. Imperfect information matters because tracking has uncertainty. Predictions can be wrong, and operators may not share enough data quickly enough. When an active satellite dodges, it burns fuel. That fuel is finite, so operators make trade-offs: dodge too often, and shorten mission life, dodge too rarely, and accept growing risk. The key trade-offs: pros, cons without cheerleading. Space activity trades economic value against shared safety. Mega constellations can deliver broadband imaging and resilience. They also multiply the number of objects that must be tracked and coordinated. Regulation trades speed for order. Loose rules accelerate deployment, but externalize risk onto everyone. Tight rules reduce risk, but can slow innovation and raise costs. There is also a transparency trade-off. Sharing precise orbital data improves safety, but some operators and governments treat data as sensitive for commercial or security reasons. Common myths and misreads. Myth: space is infinite, so debris cannot matter. Useful orbits are specific corridors. Crowding is real where missions cluster. Myth: collision avoidance solves the problem. Avoidance protects active satellites, but does not remove dead objects or old rocket bodies that are often the most dangerous. Myth: a single collision would end space use overnight. The risk is usually gradual: higher operating expenses, more lost satellites, and more uncertainty, not an instant blackout. Myth: debris is only a technical issue. Debris is also governance, incentives, coordination, and enforcement. Risks, limits, and safeguards. The most significant risk is a collision between large objects that creates long-lived fragments in a heavily used band. Even if most fragments eventually decay, the interim can be costly and destabilizing. Safeguards include end-of-life disposal, passivation of rocket stages to reduce explosions, collision avoidance coordination, and design changes that reduce fragmentation on failure. These measures help, but they require compliance and verification. A hard limit is that cleanup is difficult. Grabbing a tumbling rocket body in orbit is not like towing a car. It is precision engineering with high consequences if something goes wrong. A simple framework to remember. A repeatable mental model. Treat orbit like a shared motorway. Density: how many objects are in the lane? Control: how many can steer? Visibility: how good is the tracking data? Rules: who has the right of way and who enforces it? Cleanup: what happens to broken vehicles? If density increases while control, visibility, rules, and cleanup are insufficient, the risk compounds. What most guides miss. Most guides focus on the number of objects. The deeper issue is liability and incentives. The operator who spends more on disposal and safer design carries the cost. Now, while the benefit is shared across the entire orbital community. That is a classic commons problem, and it does not fix itself. Another overlooked point is that the most dangerous objects are often older satellites. They are the old, massive rocket bodies and dead satellites that cannot maneuver. They are big targets moving fast, and they sit in the same corridors as modern systems. Finally, debris risk is not only about accidental collisions. Deliberate destruction in orbit, even if rare, can create broad collateral risk for civilian infrastructure. The orbital environment does not care why fragments exist. Why this matters: satellites underpin navigation, timing, weather forecasting, communications, Earth observation, and military sensing. Even if most people never think about orbit, they rely on systems that do. In the short term, the main effects are higher costs, more collision avoidance maneuvers, and occasional satellite losses. In the long term, the risk is that certain orbital corridors become so hazardous that missions become less reliable, more expensive, or impossible without major redesign. Signals to watch include major collisions, new disposal mandates, active debris removal demonstrations, changes to mega-constellation licensing, and international agreements on responsible behavior in orbit. Real-world impact. The limited terrestrial infrastructure forces a coastal community to rely on satellite broadband. If a constellation loses capacity due to debris events, connectivity becomes patchy and expensive, affecting school, clinics, and small businesses. A logistics firm relies on precise timing and navigation for routing and inventory tracking. Small degradations in satellite reliability force expensive backups and reduce efficiency. A climate research team depends on frequent Earth observation passes to track fires and storms. Losing satellites is not just a commercial hit, it can weaken early warning and public safety decisions. A defense planner worries about surveillance gaps. When critical systems face collisions and uncertain operating conditions, the risk of debris becomes a national security issue. The road ahead. Space debris will not be solved by one breakthrough. It will be managed through rules, incentives, tracking, and gradual cleanup. If states and firms accept that orbit is infrastructure, not a free landfill, the fork in the road is between rapid deployment with thin safety margins and a more mature orbital economy that prices risk and enforces disposal. The first path can look profitable until it fails. A reader is applying this well when they ask, which orbits are crowded, which objects cannot move, how good is the tracking, and what rules force responsible behavior? More insight, less noise, Explore the full range at taylortaylor.co.uk.